Welcome back to another day here in our Math 32 summer session. We'll be taking on a couple more topics in probability to get ourselves used to notation and some of the setups that we'll be using later in the semester. As I was hinting at last time, whenever we take on a new concept in probability, it's probably for the best to go with a very simple setting at first and then move on to harder examples. And thus, as you can imagine, from time to time, we'll be talking about flipping a coin. Unless otherwise noted, we'll say that the probability of heads is 50% or 0.5, and the probability of tails is 50% or 0.5. Now, as a side note, I remember one of the first times I was teaching statistics, I kept using the phrase, "What is the probability of getting heads?" And the students behind me would keep giggling. Later on in the lesson, I would say, "What's the probability of getting tail?" And the students giggled some more. Go figure. Notice the caption in the bottom right. Maybe I should turn on the slideshow for a bit. How to flip a coin in 11 steps. Okay, so something that you might not have thought about for a while, but in the late 1800s, when this field of statistics was coming into maturity, there had to be a foundation of how do we think about these problems. And the second that we thought about flipping two coins, we had this dilemma. Statisticians had this dilemma. And let me just read off the slide here. How should the sample space for a trial of flipping two coins be represented? Do we have this three element space that's two heads, mixed, or two tails? Or in the bottom right, do we have HH, HT, TH, and TT? So go ahead and think about that and go ahead and make your guesses in the chat room. And the folks in chat have a strong majority, a super strong majority, and a few sarcastic answers, understandably. One of the questions that came up in chat is this like permutations and combinations? Yes, the order matters. That is in the middle of the bottom set there. The HT is different from TH in this train of thought. The order matters. So, as you understand, historically, or let me come back to this. What happened in the late 1800s, keep in mind this is before everyone had computers. The statisticians would literally flip coins over and over again. In fact, the most um, meticulous Badui brother allegedly flipped a coin 10,000 times to study it. So at least when it comes to the notion of flipping two coins, this is going to be what's called our universal set. The set of all possible outcomes for an event is called a universal set. It is usually denoted by the Greek letter capital omega. So as you have stated, the universal set of all outcomes for two coin flips is as seen on the screen there. just thinking ahead, just so you know, the first half of this lecture is admittedly just all slides. The second half of the lecture, I'm going to try to do something brand new and maybe fall flat on my face. So we'll see how that goes. So now, for more notation, there's the notion of a complement. If A is a set and subset of a universal set, then the complement of A is a set of outcomes that is in the universal set, but is not in the set A. So you'll notice that the way the notation goes, for whatever we're calling a complement, and I assure you we're going to see plenty of examples of this today and Friday. For whatever we call a complement, the notation I'll be using this semester is placing a lowercase c in the top right of the capital letter, so a lowercase c in the exponent spot. Actually, let me just go ahead and jump straight to the promised maybe good, maybe fall flat on my face thing. I recently, and by recently I mean about an hour ago, found this program called Sketch.io. Let's suppose that this is our universal set, just a bunch of random dots in this rectangle here. See if I could figure out how everything works. And that's going to be our set A. So, just as a thought process for yourself, think what the so-called complement will be. What do you think that's going to look like? That's not good. And that would be a complement. And just so you don't make a silly mistake in this later, like I would, in probability, complement is spelled with an E in the middle. It's different than paying a compliment to that person you're trying to get with at a party. And yes, I see the comments in chat. I will also try out Microsoft OneNote. Sarcastic response to the person in chat: if you misspell compliment, you take this class again next semester. Okay, so go ahead and I just kind of want to see where you're at mentally. Go ahead and try to answer this question in the chat room. And as the folks in chat are saying, that the in this particular example, the complement is represented by choice D, the elements 1, 3, and 5. That is the elements that were not in the original set. Good job. Now, there is a concept called independence. It's kind of filled with subtleties, in my opinion, so I'll be introducing the concept over and over again through several lectures, but just for the sake of having this in the notes and start talking about the concept, we say that two events A and B are independent if the probability of them happening together simultaneously can be computed by simply taking the product, the multiplication of their individual probabilities. So as we go through the semester, we'll be seeing more and more calculations with this concept of independence in mind. But for now, I just want to show you that you probably do understand this on some level with another chat query. So go ahead and try out this situation here. So as the folks in chat correctly observed, if the probabilities that we state at the beginning, one half for the probability of heads, one half for the probability of tails, and we're flipping the coin 3 times, then by the notion of independence, we are assuming that each coin flip is independent from the other one. That is, the first coin flip does not affect the second coin flip, which in turn does not affect the third coin flip, etc., etc. We simply multiply those numbers together. 1/2 times 1/2 times 1/2 equals 1/8. And you got choice B as in boy for 1/8. That is awesome. Okay, so let's see where I am in the slideshow. So what I'm going to clumsily try to show you now is De Morgan's Law. So let's go ahead and bring back the sketch pad. Yeah, you're right. It'd probably be faster for me just to show you a YouTube video at this point. Oops. Alright, so let's say that the first one is our set A, and the second one is our set B. Why doesn't my scroll wheel work here? There we go. So now what I was trying to show is De Morgan's Law. And we'll look at that left-hand side. It says we're going to first look at the union. So we're going to combine these two. We're going to take that triangle and that square. And we have our union. Like that. So the technical definition of a union is that as long as a point's included in at least one of the set, it's in the final product as well. Let me see if I can move that. Okay. Now, on the left-hand side, the notation says we have the union of A and B. Oh, sorry, it's the union of A and B. Yeah. And then the complement of that. So now, furthermore, from this purple shape, what do you think the complement of that would be? So we have that triangle, We have that quadrilateral. We're trying to get A union B complement. And remember, complement in some sense is the opposite of what we had before. So what would be the opposite of this purple shape here in the top right? And there we go. So to say that again from the start, set A, I am saying set A is the blue triangle. Set B is the red square or the red rectangle. The union is this triangle and rectangle put together that has shaded in the top right. The union is the purple shaded region in the top right. And then finally, the complement of that union is the opposite of that. Everything shaded outside of that union. The question in chat is, does the union have to have redundancy? No. The shapes might not overlap in the first place. If the shapes are disjoint, then the union has no redundancy. So now let's look at the right hand side of De Morgan's law. Let's see, how do I do this? I think I want to go this way. So once again, we have our sets A and B. Now what I want to do is show you the complement, but of each set individually. What would be the opposite of B, and what would be the opposite of A? So now, what we're going to do is, what's these last two pictures that I have on the bottom here, we're going to intersect them. The technical definition of intersection is to include the points that were in both of these sets, namely both blue and red. So this side of the equation of the De Morgan's law says A complement intersect B complement, A complement and B complement. Which points are in both the the blue and red region that I have here towards the bottom of the screen. And that's here. So what De Morgan's law says is that in either of these routes, we end up at the same place. Namely that purple monstrosity that I ended up with. I probably did get a bit ahead of myself. I have taught mathematics at all levels from first grade all the way up to college senior, but I know firsthand that not every single topic is really taught to you because, school year runs out of time or you run into standardized testing and whatnot. I maybe assumed everyone knew what an intersection and union was, or it's just something you haven't seen in a long time, and that's understandable. So, yes, to clarify some of the language, union corresponds to the logical or, intersection corresponds to the logical and. Are there other questions from the folks in chat? One of the reasons why we math teachers, such as myself, try to show you these ideas and diagrams at times is called an abstraction. If you understand how things work in the abstract sense, going back and doing things in calculations should be relatively easy. Whoa, that's not good. I probably should take a step back, and fortunately, I have time anyways. Let me get my setup going again. So we have our sets A and B. The union would be these here. And that's the intersection. So in other words, the union is bigger than the intersection. Bigger or equal to in size. I'm saving these pictures so that I could upload them to cat courses later. And you know, if I spend a whole 5 minutes doing something, I don't want to waste my work. So yes, to make it connections possibly to the computer science learners out there, union is either, union is or, intersection is both. For those who study logic, the ones and zeros, remember, intersection is harder to achieve truth values than union. How about thinking about it this way? If you're on the city streets and you're asking for the intersection of Olive and G streets, where is that? Your brain should only think about that square. The intersection of Olive and G streets should be that square surrounded by the crosswalks. It does not include the entire G street or the entire Olive street. Now, another tougher train of thought that we'll be dealing with over the course of the semester is just the notion of what is probability to begin with. And as we're going through the semester, we'll hopefully reveal or get a better understanding of this. But just for the sake of getting some definitions out there, let me read off this slide. The frequentist approach is that we assume that if we run an infinite number of trials to observe an event C, if n is the number of trials and C is the number of times that we observe the event C as we conducted trials, then as n increases, the probability of C is that limit. So in easier terms, if we could conduct an experiment such as flipping a coin many times, we simply say that the probability is what we understand to be the fraction of times that we have that observation. And again, this is called the frequentist approach. On Friday, we will be looking at something called the Bayesian approach, which is a big topic of debate amongst the statisticians out there. So, I forget why I had this lecture short in the previous semester, but that's actually going to be the end of this quote unquote hour. So let's go ahead and take a break here. And I'll see you in another 10 minutes.